Welcome back to Module 2 of our course on highway engineering. In the previous module, we explored the fundamental design aspects of highways, including route location, geometric design, pavement structures, interchanges, freeway networks, and cross-sections. We focus primarily on planning and design considerations. In this module, we shift towards the construction, maintenance, and operational aspects of highway engineering. We will discuss the design, construction, and maintenance of culverts, the design of drainage appurtenances, the different cross-sections of roads from a construction perspective, and the types of construction equipment used in roadworks. Finally, we will emphasize the importance of practical training, both in design studios and on-site, to bridge the gap between theory and real-world application. Let's begin with culverts, a critical yet often underestimated component of highway infrastructure. 1. Design, construction, and maintenance of culverts. Culverts are structures that allow water to pass under a road, railway, or embankment. They may appear simple, but they are vital to the durability and functionality of highways. A poorly designed culvert can lead to erosion, road collapse, or flooding. 1.1 Functions of culverts. Drain surface runoff and prevent water accumulation on road surfaces. Carry streams or drainage flows beneath the highway. Protect the stability of embankments and road foundations. Provide passage for animals or even pedestrians in rural areas. 1.2 Types of culverts. Pipe culverts, round, elliptical, or box-shaped, generally used for small water flows. Box culverts, rectangular in shape, constructed of reinforced concrete, used where larger discharges must be accommodated. Slab culverts, flat slabs over open channels, economical for short spans. Arch culverts, with an arch top, transferring loads efficiently, often used for aesthetic or historical applications. Bridge culverts, function both as small bridges and culverts. 1.3 Design considerations. Hydrological data, volume, velocity, and frequency of water flow. Hydraulic efficiency, ability to pass the design discharge without causing flooding. Structural strength, capacity to withstand road traffic loads. Durability, resistance to erosion, scouring, and chemical attack. 1.4 Construction of culverts. Construction typically involves excavating foundations and preparing bedding, laying pipes or casting reinforced concrete in place, providing head walls, wing walls, and aprons to control flow and prevent erosion, compacting backfill around the culvert to support the road structure. 1.5 Maintenance of culverts. Regular inspection and maintenance are crucial. Common problems include blockage due to debris or siltation, structural cracks in concrete or corrosion in steel pipes, undermining due to scouring. Maintenance may involve clearing blockages, repairing cracks, relining pipes, or reconstructing damaged sections. 2. Design of drainage appurtenances. Effective drainage is one of the most important aspects of highway engineering. Water is often called the enemy of roads because it weakens soils, erodes materials, and accelerates pavement failure. 2.1 Objectives of highway drainage. To quickly and safely remove surface water from the roadway. To prevent infiltration of water into the pavement and subgrade. To protect embankments and cuttings from erosion. To ensure safety by preventing hydroplaning and reduce skid resistance. 2.2 Surface drainage systems. Side drains, open channels parallel to the road to collect runoff. Catch basins and inlets, collect water from the pavement and direct it to storm sewers. Median drains, used in divided highways to collect water in the central reservation. 2.3 Subsurface drainage systems. Longitudinal drains, perforated pipes below pavement layers to intercept water. Cross drains allow water to move from one side of the road to the other. Filter drains, gravel trenches that facilitate drainage while preventing soil migration. 2.4 Appurtenances. Drainage appurtenances are supporting structures such as Headwalls and wind walls prevent soil erosion around culverts and channels. Energy dissipators, structures like steeling basins to reduce flow velocity. Check dams, small barriers that slow down water and reduce erosion. Properly designed drainage systems significantly extend the life of highways. 3. Different cross-sections of roads in construction practice. Earlier, in Module 1, we examined the theoretical cross-sections of roads. In construction practice, however, engineers must implement these designs in the field. 3.1 Embankment cross-sections. Where the road is raised above natural ground, embankments are constructed. Key considerations include soil compaction to achieve strength and stability, side slopes protected by turfing, stone pitching, or vegetation, adequate width of embankment crest to support road and shoulders. 3.2 Cutting cross-sections. In hilly or mountainous terrain, roads may be constructed in cuttings. Key aspects include proper slope stabilization using retaining walls or rock bolts, drainage channels to prevent water accumulation, benching in steep slopes to improve stability. 3.3 Pavement cross-sections. Field construction involves laying successive layers. Subgrade, compacted soil. Subbase, granular or stabilized material. Base course, stronger layer to spread loads. Surface course, asphalt or concrete for direct vehicle contact. Field tests, such as density and moisture content checks, ensure compliance with design specifications. 4. Construction equipment types. Highway construction is heavily dependent on specialized equipment. The choice of equipment affects cost, speed, and quality. Four point one Types of pavement. There are two major types. Flexible pavements, made of bituminous or asphalt layers. They distribute loads gradually through successive layers of subbase, base, and surface course. Rigid pavements, made of concrete slabs. They distribute loads over a larger area due to slab action. 4.2 Pavement design factors. Design depends on traffic loads, both the number and weight of vehicles. Subgrade soil strength, poor soils require thicker or improved pavement layers. Climate, temperature variations, rainfall, and freeze-thaw cycles affect performance. Durability and cost, balancing initial construction cost with long-term maintenance. 4.3 Structural design. Pavement thickness design uses methods such as empirical methods based on road test data. Mechanistic empirical methods considering stresses, strains, and material behavior. Ultimately, the goal is to provide a pavement that lasts its design life, usually 15 to 30 years, with minimum maintenance. 5. Interchange design and spacing. In urban and freeway context, interchanges replace intersections to maintain uninterrupted traffic flow. 5.1 Types of interchanges. Diamond interchange, simple, commonly used for low to moderate traffic. Cloverleaf interchange, handles high volumes without signal control but requires more land. Trumpet interchange, suitable where a highway terminates at another. Directional interchange, complex, used for major highways with heavy turning movements. 5.2 Spacing of interchanges. Spacing must be carefully planned. Too close, and drivers have insufficient distance to weave, merge, or exit. Too far apart, and accessibility is compromised. Standards vary, but typical minimum spacing in urban areas is about 1 to 2 kilometers, while rural freeways may have 3 to 5 kilometers between interchanges. 6. Highway information systems. Highway information systems are computer-based tools that assist in planning, design, maintenance, and management of highways. They are often part of a broader Geographic Information System (GIS). 6.1 Applications. Storing and managing data on road networks. Traffic analysis and forecasting. Pavement condition monitoring. Environmental impact assessment. Optimizing maintenance schedules. By integrating spatial and statistical data, this helps decision-makers allocate resources more efficiently. 7. Freeway networks and safety. 7.1 Freeway networks. Freeways are high-capacity, access-controlled highways designed for uninterrupted flow. Their networks must be carefully planned to connect major cities and economic centers. Provide redundancy so that traffic can be redistributed in case of blockages. Balance national, regional, and local needs. 7.2 Safety considerations. Highway safety is a crucial aspect. Common measures include adequate lane widths and shoulders, median barriers to prevent head-on collisions, guardrails at dangerous sections, road markings, signage, and lighting. Intelligent transport systems, ITS, such as speed cameras and traffic sensors. Road safety audits are often conducted during design and after construction to ensure hazards are minimized. 8. Different cross-sections of roads. The cross-section of a road determines how space is allocated for vehicles, pedestrians, and drainage. 8.1 Rural roads. Typically simple, with 2 lanes, shoulders, and side drains. 8.2 Urban roads. Often include sidewalks, cycle tracks, parking lanes, and wider medians. 8.3 Expressways. Feature multiple lanes, wide medians, service roads, and controlled access. Cross-sectional design must balance cost, land availability, and expected use while ensuring safety and durability. Conclusion to Module 1. We have covered the essential engineering and design aspects of highways. We started with route location and surveys, which determine the best possible alignment for new roads. We then explored geometric design, which shapes the physical form of highways, and pavement design, which ensures structural durability. We discussed interchange design and spacing to manage traffic flows, followed by highway information systems and freeway networks. Safety and different road cross-sections were highlighted as critical to functionality and user comfort. In Module 2, we will shift focus to the construction and maintenance aspects of highway engineering, covering drainage design, culverts, construction equipment, and the integration of field and studio practice.